everyone, so today what we are talking about is paper chromatography. And pretty much what this is, it's just a way to separate mixtures and identify them on a piece of paper. So I'll explain here a little bit more. So what we have, first of all, is we have this little strip of paper, okay? And the thing we might be trying to identify is some sort of liquid, okay? It could be like a Kool-Aid mixture, or it could be ink. Okay, we might just want to identify what is inside of this liquid. So what we'll do is we'll take this thin little strip of paper, sort of like this guy, okay? We'll take a thin strip of paper like this, and what we'll end up doing is we'll put the liquid or ink as a little dot on the bottom of the paper, okay? This is known as the stationary phase. Right, it's on stationary, so it's the stationary phase. Okay, it's not moving, it just stays put. And then what we do is we end up putting it in a beaker with some liquid in the bottom. Okay, this is known as the mobile phase. Alright, and what that does is that liquid attaches to this paper and starts to climb up this paper, and while it's climbing up, it'll separate this ink into different parts. And I did this earlier with a marker, and it originally looked like this, and then after I set it in the beaker, it ended up looking like this. So the ink traveled up and then left, as you could see a little separation of red ink and green ink here. I ran out of room, but if I had a longer piece of stationery or chromatography paper, it would have separated even more. So then what we do is we just put these together, and then you'll see that separation of that ink. One thing that we have to be aware of is that polar liquids move polar liquids. Okay, so I used ink, a washable marker on this, and then this liquid that I used was just water. So water's polar, that washable ink is polar, so it was able to move it, okay? If I put a non-polar substance in there, the ink wouldn't move, okay? So that tells us right away if we put a polar, right, if we put a polar liquid in here and it moves our ink upward, that means that the ink is polar as well, okay? This could be non-polar and non-polar, it'd be the same thing. Non-polar liquids will move non-polar liquids, right? So we got to know the difference between polar and non-polar. H2O, right, that guy is polar, mainly because when we draw him out, he's got those central atoms there that make him uneven, give him that pull, that uneven pull. Non-polar are ones like isopropyl alcohol. Okay, these are non-polar. So this is what we typically use to move non-polar inks and solvents. Okay, we use isopropyl alcohol, which is just rubbing alcohol nail polish remover. Okay, most alcohols are less polar, non-polar. Okay, some example of something that is non-polar is methane, right? It's got an even pull from all those atoms, so it is non-polar. There is no net pull. But this guy's got those lone pairs on the central atom, so that one is always going to be polar. So then you might be asking, okay, how does this help us identify things? Well, first of all, we'll know if the substance is polar or non-polar based on which liquid moves it, right? If a polar liquid moves it, it's a polar ink. If a non-polar liquid moves it, it is a non-polar ink or liquid. But there's something else we can do, and it is called the RF value, okay? This helps us identify numerically what a certain substance is. Okay, so RF value is just distance traveled by solute, which in this case is our ink, okay, over distance traveled by solvent, which in this case was my liquid or my water. Okay, so RF value is pretty easy. It's just how far the ink traveled over how far the liquid in the beaker traveled. So an example of this, I might have my chromatography paper, okay, and it starts right here at this dot. I might draw a little line to help me know where my starting point was, and what will happen is the water will start to travel up this guy. We'll say he's in the beaker, and the ink will move this far, okay, so the ink will move this far, but the solvent or the water will move that far, okay? So let's say that we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 dots, and each of those dots is a centimeter. So we'll have 12 centimeters on top, and this will be 1 centimeter on bottom. It's not at the very bottom, okay? So what we do is we just figure out the distance the ink traveled and put that over the distance the solvent traveled, okay? So when you're measuring the ink, how far it traveled, you gotta go from the center of the dot, or you gotta try to distribute that ink in half. So if I'm looking at this guy, I'm gonna go somewhere right in the middle of it, okay? That looks like about a middle distribution of those inks. So right here, I'm gonna put a 0 and I'm gonna go across, and that's pretty much 1, 2, 3, 4, 5, 6, 7, 8. This is actually 13. 8 centimeters. So my top distance is 8 centimeters. So now we gotta do distance traveled by the solvent. A common mistake people make on the AP exam is that they'll measure all the way to the top of the paper. Okay? It's where the water traveled or the liquid traveled. So here our liquid traveled to about 12 centimeters. So let's go ahead and we'll put 12 centimeters right there. Again, remember I changed this to 13. Now it traveled up to 12. Okay, so 8 over 12, that's about an RF value of 0.66. Okay, no units, just an RF value. And then what we can do is we could look up a table of RF values. You know, Kool-Aid might have an RF value of 0.55. Black ink might have a RF value of 0.75, and then maybe a marker, a black marker, might have an RF value of 0.70, and out of all those we would say, hey, this is pretty close to a marker. Okay, so my RF value will tell me that this is the ink that was on my chromatography paper. Okay, so we have a set of known RF values. We solve it ourselves by taking distance of ink traveled over distance of water traveled, and then that way we could solve for RF value. Okay, a lab over this is coming at you real soon, so be ready for that.